subscribe.
Hey y'all, welcome back. So today we're talking about continuity and the different kinds of discontinuities that exist in certain functions. So in this first problem, it's asking us to find the values where the function is discontinuous and classify the discontinuity as removable or non-removable. So just to kind of talk about that briefly, a removable discontinuity is one where basically you have a hole. Okay, so in other words, like if there's a break in the graph where it's just a single point that is preventing the discontinuity and it's continuous otherwise, meaning like the left-hand limit is equal to the right-hand limit, then that is a removable discontinuity. But visually, it just looks like a hole. The different kinds of non-removable discontinuities that we'll see here is either going to be where you have a vertical asymptote or a jump in the function. In general, the non-removable discontinuities are ones where the left and the right-hand limit do not equal each other, or maybe do not exist. So let's take a look at number one. It says that we've got the absolute value of x minus 2 over x minus 2. This is going to have a discontinuity at x equals 2. It's pretty easy to see why here. If I set the denominator equal to 0, which you can't divide by 0, I get a value of x equals 2 that would cause this function to be undefined. Now this is a specific function. I called it the jump function when we went over it in the notes. And basically what this kind of function looks like, just to kind of give you a visual idea of what's happening here, is you're going to have like a line, a horizontal line, where this thing equals 1, right? Anytime that this value becomes positive. So in this particular problem, this little break is going to happen at x equals 2. Now at x equals 2, it is undefined, so we should have like an open circle here at 1 and negative 1. And so basically the graph's going to look like this. Okay, and so we went over how to graph a function like this in the notes, and I would recommend you go back and review that if you want a little bit more detail here. But you can see that the left-hand limit and the right-hand limit do not agree at x equals 2. This is a pretty rough sketch here, but oops. Just really trying to get rid. There we go. And so you can see that, the left and the right-hand limits do not agree. They are not equal to each other. And so then we say it's a non-removable discontinuity. So this would be where the discontinuity is. One way to, I guess, like if we're going to kind of clean up how we're going to answer these questions, I'm going to say that there is a non-removable discontinuity. Let's see if I can spell discontinuity at x equals 2. Okay, and I'm also going to give just one slight bit of more detail here. I'm going to call this a jump. You don't need this phrasing. It's enough to say there's a non-removable discontinuity, but I think it's at least in the beginning when you're first learning about the difference between a removable and non-removable discontinuity is to give a little bit more detail on what kind of discontinuity it is, more so than non-removable and removable. So that way, as we go through these, you'll be like, oh, a jump is always a non-removable discontinuity. A hole is always a removable discontinuity, and so forth. So for B, we do need to set the denominator equal to 0 and solve, just like on A. This is a quadratic that it appears that we either need to factor it or we need to use quadratic formula. I do believe this is factorable here. Let me think about this for a second. Let's see, we could do 6x. Yeah, 6x, let's try this. 6x minus 1 times x plus 3. Now let me double check and make sure that actually works. So let's see here. We've got 6x squared, so that's gonna check out for the first term. Negative 3 checks out for the last. Now for the middle, we've got 18 minus 1, so yeah, these will be our two factors here. That means that we're gonna have two places where this function is not continuous. One location is going to be at 1/6, and one location is going to be at negative 3. Now I want you to think back to our unit on rational functions, where we discussed, what happens at these x values that make the denominator 0. If it is, in most cases, it's going to be a vertical asymptote, but if it is also a value that makes the numerator 0, like this x equals 3, then that is going to be a hole. So in other words, like this represents a vertical asymptote, and this particular x value, there is a hole in the graph. Okay, so we actually get one of each. We get a removable and a non-removable discontinuity. So let's make sure, let's go ahead and answer this question. So we're going to say that there is a non-removable, so this is the vertical asymptote, discontinuity. Make sure you guys can see this okay. Yeah, okay. At x equals 1/6. And that particular kind of non-removable discontinuity is a vertical asymptote. And there is a hole, which counts as a removable discontinuity. At x equals negative 3. So let's go ahead and box our answer here, and we'll take a look at the next problem. Okay, this one is the natural log of the absolute value of x. Now, I'm not going to really expect that you know what this looks like, but I want, just right off the bat. But I do want you to kind of think about this. So basically what's happening here is we have our, let's just say it was y equals natural log of x. Okay, so hopefully, it's been quite a while since you've had to graph this, so I have no problem with you looking at this graph on the calculator just to have a better idea of what's happening here. But the natural log, or just really any logarithmic graph, is going to be the inverse of an exponential graph. So it's usually going to look something like this. Okay. Now, if it's the natural log of the absolute value of x, that means that for every input that I plug into x, even if it's negative here, so like the natural log of, let's say 2, will equal the natural log of negative 2, because it's going to take, this function is going to take the absolute value of whatever the input is. So whatever negative values that I input here are going to be basically like changed to positive, and then take the absolute, and then take the natural log of that. So in effect, what happens is every single negative x value now has an output. Okay, and so you're going to have this exact same curve, but reflected over the y-axis, and so the natural log of absolute value of x is going to do something like this. Now, like I said before, I don't really care if you want to take a look at the graph in the calculator. In fact, let me go ahead and pull one up just so I can kind of guide you through how you would type this in. Absolute value is not something that's like really obvious how to do, so you're going to go to y equals here. Now, there's a couple different ways you can get to the absolute value, but I like to just hit math, and then, where is it again? Let's see. There we go. Scroll over to number, and there should be this first option, absolute value. So you just hit enter, and so we're just going to, I didn't put natural log. Let's do that first. Let me clear that out. Natural log of the absolute value, so going to go over here to num, so the absolute value of x. So that's how you would type it in the calculator. Now you can look at the graph and see that it looks kind of like what I've drawn. Now you do kind of run the risk when you just look at this without really thinking about what it is. It kind of looks like these come together to a point, but that is not what's happening. In fact, if we zoom in a little bit, maybe we can see that these are not actually intersecting each other, but instead are approaching this vertical asymptote at x equals 0. Here's maybe I need to have sort of a custom zoom here to really see it. So I'm going to zoom out here and just kind of scroll down a little bit and zoom a little lower in here so you can see that they're not intersecting. So just kind of getting a little bit lower here. I don't even know, it's so close to 0 you probably can't even see it. I have to zoom in even further, I guess. Yeah, these TI-84s are a little bit limited. Yeah, I really don't like that. Let's sort of shift gears here. Maybe looking at the calculator is not going to be a very good idea at all. So let me get rid of this calculator, and instead let's grab this in Desmos, shall we? So I'm just pulling up Desmos here. I'm going to type in the equation. And you can see a little better here. Gosh, they really come together. These values get very close to 0 very quickly, but if you zoom in, you can see they don't actually get quite on there. And what's really happening here is this graph is just approaching that asymptote on both ends. But 0 is never defined. The natural log of 0 has no value, so so we can determine there is a discontinuity there. It's not like these things are coming to a point of v and then coming back up. So anyway, our answer here is going to be that we do have a discontinuity at x equals 0. And specifically, it will be a non-removable discontinuity. And this particular removable discontinuity, so we're, pretty much all of these are going to be either jumps, like we saw in part A, or a vertical asymptote, like we saw in part B. This particular one's a vertical asymptote.
All right, so looking at 1D here, we see right away we've got a 1 in the numerator. So that means that we're not going to be able to have any holes here. There's not going to be any removable discontinuities in this function. So we're really just looking for those non-removable discontinuities or those vertical asymptotes. So I'm going to set the denominator equal to 0 here and solve it. And hopefully you're going to see real quick that we're not going to get any real solution here. If x squared equals -1, the next is just going to be plus or minus the square root of -1. So it's just going to be plus or minus I, which means that there's no real solution here or no real valued x that can make the denominator equal 0 here. So what this indicates is that there's no non-removable discontinuities and there's no removable discontinuities. So we can safely say that there's just no discontinuities here. This is going to be a continuous function. So there are no discontinuities. F of x is a continuous function. Here on 1e, we can see that we have the same factor in the numerator and the denominator. So we can tell that there's definitely going to be a hole here. There's going to be a removable discontinuity at x equals -1. And there's not going to be any vertical asymptotes here because that's the only factor that's in the denominator. So just to algebraically show this, we're looking for the x values where x that would make either the numerator or the denominator 0. So x plus 1 equals 0 is going to yield x equals -1. And this is going to be our only discontinuity. It'll be a hole or a removable discontinuity at -1.
All right, well, let's take a look at f. We've got h of x equals x to the fourth minus 1, which is the difference of two squares, so we will end up factoring that one, over x plus 1. So it looks like we're going to have a discontinuity at x equals negative 1. I guess the question is going to become, is that going to be a whole or is it going to be a vertical asymptote? So yeah, let's go ahead and factor this. It is a difference of two squares. So we can start by factoring it as x squared plus 1 times x squared minus 1. And the x squared plus 1 is not factorable, so that is going to be a prime factor. But the x squared minus 1 is another difference of two squareds, so we can write that as x plus 1 times x minus 1. Okay, so it's all this over x plus 1. And so we can verify here that because we have this factor on the numerator, the denominator that's the same, that the value that would make the denominator 0 here also makes the numerator 0, and therefore is causing a hole in the graph. And so a hole means that the left and right hand limits do agree that they are equal. So the limit exists there, and therefore we have a removable discontinuity. So here we've got a removable discontinuity. I'm just going to copy this wording over here at x equals negative 1. Oops. There we go. Okay, so yeah, we've got a removable discontinuity at x equals negative 1 for f. So let's take a look at g. Now, g is a piecewise function, which means that the function is defined differently for different parts of the domain. So just to get a visual down here, just a quick sketch here. I mean, we don't need to make it perfect or anything, but we know that less than or equal to 2, the graph is just y equals 3. So basically what we're going to have here is a horizontal line when y is 3 and going all the way to where x is 2. So basically, now this doesn't really look like it, but this is supposed to be a horizontal line with a closed dot here. And then the second piece is 4 minus x. So that would have a y-intercept of 4, but it would have a slope of negative 1. So it'd go like down 1 over 1, down 1 over 1. So basically, you're going to have an open circle here, and then it'll kind of aim downwards like this, where this is at 2. Because 4 minus 2 is 2. So what we can see here is that it is not continuous. There is a discontinuity here. The discontinuity is happening at 2, and since the left and the right hand limits do not match, we're going to call this a non-removable discontinuity, and this is going to count as a jump. It's not a vertical asymptote. It's a little bit more like what's going on with number 1 here. So we do have that discontinuity at x. Actually, it's the exact same answer here. It's at 2. Look at that. So yeah, so there you go. So there's g. And that finishes off the first page here. So let's take a look at the next page. All right, for this section, we're trying to find the values of k that make the function continuous. So basically, we've got two pieces of a piecewise function that potentially have a break at x equals 2. So like at x equals 2, we stop referring to this function, which will be when x is less than 2, and start referring to this second function when x is greater than or equal to. So in order for it to be continuous, since both of these pieces individually are continuous, there's no break. I mean, these are both polynomial functions here. The only break is occurring at 2. And so what we need is for the y value at x equal 2 to be the same for both of these pieces. So we're going to set up an equation saying, okay, well, both of these pieces need to be equal. They need to have the same output or the same y value at a particular x value. We don't necessarily need them to be equal for all x values. We just need them to be equal at the x value where the break is potentially occurring. So at specifically x equals 2. So I'm going to substitute in 2 for all these values of x, and then solve for k. Okay, so let's go ahead and start simplifying this. We got 2 squared is 4, so 4k plus 4 equals 8 minus 2k. So I want to collect my terms here. I'm going to add 2k to both sides to make that 6k. And I'm going to subtract 4 from both sides to, we get 8 minus 4 is 4. And so k is 4/6, which reduces to 2/3. And so if k is 2/3, then this function is continuous.
And for 2b, we're trying to do the same thing. We're trying to make this function continuous, and we're trying to find the k value that'll make that happen. So just to give you a little bit of a visual here, let me pull up this graph on Desmos for you. And you can see that the red section here, this graph is for when x is less than 0, and the green one is for when x is greater than 0. And what we're trying to do is make this continuous by picking a value for k. It's got to be the same value for both of these pieces in the piecewise function. And so what I've got here is a slider so you can kind of see what would happen for different values of k. You can see as k decreases, these two pieces get further away from each other, but we're trying to make it continuous. So what we want is for these two pieces to connect, and it looks like they're going to connect if k is, it looks like 2.5, but we want to verify that algebraically. So let's go ahead and go back and see how that would work out. Just like with part A, we want to set these two pieces equal to each other for when x is 0. So k minus 0 equals 5 minus k. And so we end up with k equals 5 minus k. Adding k to both sides gives me 2k equals 5. And then if we divide both sides by 2, we're going to get k equals 2.5, which is what we saw visually. It's nice when your algebraic answer matches up with your graphical answer. So yeah, there's 2b.
Now for C, same thing here. Okay, we're going to set the two equations equal to each other. So natural log of x plus 3k equals 2x plus k. We want it to be continuous, so we need to make sure that when we break over from one function to the next, that the y values are the same, so that there is no break. So we get the natural log of 1, and then we got 2 times 1 over here. So the natural log of 1 is 0. Come on. There we go. And you can go back to our unit on logarithms if you just want some clarification there. But yeah, the log with any base of 1 is going to be 0. 2 times 1 is 2. So what I'm going to do is collect my like terms by subtracting k on both sides. So I get 2k equals 2. So k here is going to be 1. So if k is 1, then we have a continuous function, even though it's a piecewise defined function. For number 3, we're doing a very similar kind of thing here, except the only catch here is that we've got 3 pieces instead of 2. So we need to be able to simultaneously connect the first 2 pieces to the second 2 pieces, meaning like when x is -1, where the first break occurs, this needs to be equal to this, or the y values need to be the same. But also at the second break, at x equals 3, this equation needs to have the same value as this. So we actually end up with like really like a system of equations here. So let's see how this plays out. So the first one would be 2x equals ax plus b, and we want those to be equal when x is -1, because that's when that first break is occurring here. I'm getting that from right here. So I'm going to plug in -1 into x. And notice here I've got 2 variables, right? So I really cannot solve this yet. I can simplify it. So I'm going to say that it's 2 equals -a plus b. And then for the second equation, at the second break, we've got ax plus b equals 2x. And we want that to happen when x is 3. So we're going to have 3 times a plus b equals 2 times 3. And so once I simplify that, I get 3a plus b equals 6. Now, individually, I can't solve either of these two equations, but I can group them and solve them as a system of equations. So I'm just going to make a little note here. I'm going to say solve this using a system, or I'll say solve for a and b using a system of equations. So the system here is going to be, I'll just borrow these equations real quick so I don't have to retype them. But we get 3a plus b equals 6 as one of the equations, and then the other equation is going to be this one right here. And I'm just going to rearrange it a little bit so that it looks similar to the other equation. In other words, I'm just going to put the equals 2 on the other side. Okay, so here is my system. And so I'm going to solve this for a and for b. And I guess I'll do this using substitution. You could get away with using elimination, but I think substitution is probably going to be the way to go here. So I'm going to solve this first equation for b and then plug that into the second equation. So if I solve this one for b, I'm going to get b equals a plus 2. And then I'm going to take that expression, the a plus 2 expression, and substitute that in to b for the second equation. So that gives me 3a plus a plus 2 equals 6. 3a plus a is going to be 4a. Then I can, I keep typing 0 there for 6 there, I'm not sure why. So we've got 4a equals 4. So a is going to be 1. So we got a. And then we can use that a. We know a is 1, and since b is a plus 2, and a is 1, then that means b is 3. So we get a equals 1 and b equals 3 as our values that would make this piecewise function totally continuous, meaning it's continuous at the first break and the second break if we make a1 and b3. Okay, so that one's kind of I think, the system of equations problem is probably the most complicated one. Just make sure you for sure know how to make these kind of piecewise functions continuous, and you'll be in pretty good shape. If you can go a little above and beyond, you can solve number 3 here in questions like this as well. Just know that when you've got 2 breaks, it is going to sort of evolve into a systems of equations problem. Okay, let's take a look at the last page. For number 4, it says, give an example of a function with a removable discontinuity at x equals 2. So recall that a removable discontinuity is one that has a hole. So really all we need to make sure is that we've got a hole in the graph. The easiest way to do that, I think, is to make x minus 2 a factor of a rational function in both its numerator and denominator. So just make sure when we were writing this, and you did this before back in our rational functions unit where you had to come up with a function if I told you where the hole needed to be or something like that. And so this other factor could be anything. Here's a sort of a real simple example here, but your answers might vary. The key here is that you do have a hole or a removable discontinuity at x equals 2. So that's what happens when you have this factor that makes both the numerator and the denominator equals 0 when you plug in x equals 2. Okay. So key thing here, removable discontinuity, just basically means you have a hole. All right, so this is just one example of a correct answer. As long as you have the x minus 2's top and bottom, you can have kind of whatever else you want going on for factors, but keep it simple just in case you make a small error somewhere. For number 5, it says, give an example of a function with a non-removable discontinuity at x equals 2. So you have some options here. This non-removable discontinuity can either be a jump, it can be a vertical asymptote. Really what you're looking for is a discontinuity where the left and right-hand limits are not the same. But the easiest ones to deal with are the jump or vertical asymptote. So we can actually write like a very simpler function here and just not make the numerator have the same factor. So if I just like, and I don't even really need this if I'm going to do that, it's just like 1 over x minus 2 is probably the easiest way to write that, where we have a vertical asymptote at x equals 2, which would be a non-removable discontinuity. You could also do like a jump function. So you could do something, actually wasn't that the very first problem here? Yeah, so you could do like this exact same equation. It's not as interesting because I'm kind of giving it to you. But yeah, that will work too. This is like to answer the question, hey, does that work? Yeah, that totally works. So these are both 2 examples. Again, your answers may vary here. And you don't need to give me both, okay? You just need to give me one. I just want to give you an example of both kinds of these non-removable discontinuities. Like, this first one will have the vertical asymptote. The second one will have the jump. It doesn't need to be both, but yeah, you could, whichever one you like better is fine. For number 6, it says, for what values of x is the function discontinuous on this interval? Okay, so they're just giving you a graph of a piecewise function. We have a couple of different discontinuities here. We have a discontinuity at x equals 2. Now this is a jump, so this is going to be a non-removable discontinuity because the left and the right-hand limits are not equal. But at x equals 6, where we have a hole, and actually it's slightly different than the holes we've dealt with before, because it is defined here at x equals 6. Yeah, I guess we still call that a hole, though. So to be more specific, though, it is going to be a removable discontinuity. Okay, so these are going to be our 2 discontinuities here. And so I'll say there is a non-removable, and so this non-removable, I guess I'll call it a, yeah, this is a jump. Discontinuity at x equals 2, and there is a removable, I'm going to call that a hole, discontinuity at x equals 6. And those are going to be the only 2 discontinuities we have here on this interval from 0 to 8. And that was the last problem. So let me know if you guys need any extra help or if there's anything I can do to clarify how I worked any of these problems. But other than that, y'all have a great day, and I'll see you next time.